Hi, welcome to my talk, Manage Alert Overload with AIOps. In this talk, you will learn how you can leverage AI and large language models to solve one of the biggest problems when being on call, alert flooding and alert fatigue. My name is Birol, and I am the CEO and co-founder of iAlert. iAlert is a software company based in Germany and provides an incident response platform and covers everything during the incident response lifecycle, including preparing for incidents, responding to incidents, communicating incidents, and also learning from incidents. Some of the capabilities that we have are sophisticated alerting, managing on-call and schedules and overrides in iAlert, and also communicating incidents through status pages. Our solution is used by small and large companies alike across the world, and DevOps and ITOps and managed service providers use iAlert to improve their operational efficiency, respond faster to incidents, and provide a better service uptime to their customers. Before we dig into the talk, let's first start with the why. Why is it important to effectively manage? Alert overload leads to high MTTA and high MTTR, makes you less efficient, and increases stress, right? And in a situation where you don't need additional stress, because we're talking about situations where you're probably experiencing a major incident and being paged at 3 a.m. in the morning, and the last thing you need is additional stress through a mismanaged alert configuration where you're being flooded with alerts. And in this webinar, I'm going to show you how you can effectively manage alert overload using something we call intelligent alert grouping. And to set the stage, I'd like to show the results of one of our customers. Only after 2 weeks, that particular customer was able to reduce alert volume by 93% and also improve their response time by more than 4 hours. And as every minute you save in response time is a minute improvement in your MTTR. And every minute in improved MTTR leads to a better uptime. And uptime is service uptime is probably one of the North Star metrics that every SRE engineer cares about. All right, before I actually start talking about intelligent alert grouping, I would like to show you other use cases where we already have been successfully leveraging AI. And these are use cases, and we usually like to cluster things around the incident response lifecycle. And one use case that we've implemented probably 6 months ago or so is using AI assistance for on-call scheduling. This is a simple chat interface where you can just lay out your requirements, and then the AI assistant will walk you through the schedule creation process, or not walk you through, but just get all the input that's necessary. Let's say you have a complex schedule, you want to create a follow-the-sun schedule. You can just in using natural language. So that's one area where we've been using AI. Another area, probably the most obvious one, is when you want to communicate incidents to your customers, maybe on a status page. And when you want to communicate an incident, first and foremost, you don't want to spend too much time on communicating incidents, because what you actually want is reduce the business impact and solve the problem. But of course, communicating incidents also helps you focusing on the problem, because then you have less people asking what's the status, or less customer support requests. And we've embedded AI and large language models into our software, where you can just provide a few words and it'll create the entire incident for you. Use a message and a tone that's appropriate for the audience when you want to communicate incidents, and make it very easy. And another area where we're using AI is in the post-incident phase, which are the creation of postmortems. So postmortems, they are commonly used across tech teams, where they see an incident as an opportunity and try to learn from them. And a postmortem document is essentially a document that lays out what happened, the incident timeline, what actions were taken, what was the business impact, what was the root cause, and what are we going to do in the future to avoid this incident. In other words, how can we learn from this incident, right? And if you ever happen to be in a major incident, you know that, first of all, there's lots of data that's being collected. One type of data is machine-generated, monitoring tools sending constant updates. Maybe you have other automation tools that do things Then you usually collaborate in a dedicated chat channel, what we usually would call a war room. And then you collaborate on this incident and exchange a lot of information, coordinate tasks, and really collaborate on the incident. And these, like all these data, they contain lots of information, which are usually the foundation for your postmortem document. Now you can either go ahead and recreate the timeline yourself and whatever was said, whatever actions were taking, or in this area, it almost feels irresponsible not to leverage AI. Have an AI like scan through all the data, scan through your chat history, look at all the machine-generated data, and reconstruct the incident timeline, what actions were taken, what was the root cause of the incident, like based on the chat messages, and really give you an 80% version of your postmortem document. So you can spend the remaining 20% on like the most crucial phase, which is like learning from this incident and discussing with your team how to get better. And we think that's an area it's meant to be improved with the help of AI. But today we're not going to talk about these incident stages. We're going to talk about the response phase. And in particular, we're going to talk about how you can leverage AI to reduce alert fatigue and manage alert overload. This time I'm going to do something different. So usually I first lay out how we did it and talk about some theoretical concepts, how we've implemented intelligent AI grouping. But this time I would like to first show you AI grouping in action, and then, which is probably the most interesting phase, and you just see how it works. And then with the hope that it's clearer when I try to explain how we did it, because what the end result was, right? So let's start with a small demo of intelligent alert grouping. But before I start, let's quickly define what we mean by intelligent alert grouping. So intelligent alert grouping is the process of identifying alerts that refer to the same issue and consolidating them into one alert. And this reduces noise and prevents alert fatigue, prevents you from being overwhelmed to having to look at multiple alerts and seeing whether this is a new issue or whether it refers to the same issue that you were just paged a few minutes ago. So let's get into the demo. So this is, right now there are 0 alerts. And what I'm going to do now, I'm going to create a few sample alerts and see how they behave. Alert grouping is turned on right now. So let's switch to Postman. And I'm using Postman here just for this demo, but this can be any monitoring tool. So we are agnostic when it comes to monitoring. We have 100+ integrations. But for the sake of this demo and to make this a little bit more smooth and not having to jump between tools, I'm gonna use Postman and trigger a few alerts. And the first alert is about a coffee machine being down in an office. So the alert says coffee machine on floor 2 needs a caffeine boost maintenance. So let's send this alert to iAlert. And of course, what we'd expect is that a new alert is created, right? That's exactly what happens because it's the first alert and there's nothing to group. And let's now move on, create another alert regarding the same problem, but use a different wording. Alert, coffee machine on floor 2 is taking a coffee break. So it's still the coffee machine that's not working properly, but we've rephrased it a little bit. So let's send it to iAlert. And as you can see, there still is only one alert. And there's a small indicator that's animating here that says there are already 2 alerts that have been aggregated into this alert. And if we would look into this alert, we'd see which alerts have been aggregated. But as you can see, although the 2 alerts are only somewhat similar on a textual level, the AI is able to understand that, okay, these refer actually to the same problem. And let's move on with another example. Let's try to be funny and say, instead of talking about coffee, we're going to talk about Java, which also means coffee, no Java from the Java machine. Floor 2 coffee maker is down. So let's send this to iAlert. And again, here we'd expect no new alert to be created because it's the same coffee machine on floor 2. So no need to create a new alert. And as you can see here, the indicator is now 3. So there are already 3 events that were aggregated with these alerts. All right, let's provide a counter example. Let's say something else on floor 2 is broken. The water cooler on floor 2 is broken. Let's send this to iAlert. And here we expect that a new alert is created because water cooler and coffee machine are different things, although they are on the same floor. So here we can see, even though like there are some elements that are the same on a textual level, but the underlying semantics are different because one talks about coffee machines and the other one talks about water coolers. So that's why a new alert has been created. And the reason like why this is important, like even if you are like, you might not even be the recipient of the second alert. This might be a completely different team, right? And you don't want to aggregate an alert that wasn't intended for your team. So otherwise, like the team might never know that something is not working. And the alert, which is the worst case, goes completely unnoticed and you're informed by your customers that something's not working. Now let's move on with another example. Probably you're thinking, okay, these are good examples and they are easy to understand, but they don't exist in the world of tech. Like my alerts are not about coffee machines or water coolers. My alerts are about like hardware, about Kubernetes clusters, about pods not being terminated, CPU is running high, so on and so forth. All right, fair enough. So let's use a more technical alert, one that says the hard drive is full. So let's send this to alert. And as expected, a new alert is being created. The hard drive is full. And let's rephrase the same problem with different words. This time, we're not going to reuse any of the words that was in the previous alert. So the alert is the storage capacity has reached the limit of 90%. And as you can see, there are no common words between the hard drive is full and the storage capacity has reached the limit of 90%. I'm gonna send this alert. Quickly refresh, and as you can see, both alerts have been aggregated into one, so no new alert was created. So I think this example shows perfectly what we mean by like when the semantics of an alert is captured, and we're not only looking at the textual similarity between alerts. And here you can see that right now alert grouping is still in progress. The grouping window is set to 5 minutes, I believe. So if there are no new alerts, the grouping will end in a few minutes. And you can also see like the entire payload of the events that came in. You still might be skeptical because these are like natural sentences. Like these are maybe not representative for real alerts. You might be thinking my alerts are like way bigger. They contain lots of more, a lot of more information. And they might be even a little like cryptic in nature. So let's try that. So let's try, and what I'm about to do now is I am going to use alerts, actually live alerts from a production system. And these were alerts where we know that there were instances where many alerts were being created. So there clearly was a case of alert flooding, which means like in a short period of time, like maybe 10 minutes, 15 minutes, lots of alerts were created. And I think in this example, it's even 5 minutes or so. And what I'm first going to do is I am going to disable intelligent alert grouping first. So we see first the effect of, okay, alerts being created without grouping, and then we'll look at that at the same alert. We will recreate the same alerts with the grouping enabled. For this, I have configured this runner in Postman that will create 31 requests, alerts, send 31 events to our events API. And these are actually alerts from Prometheus. So again, real alerts that were generated in a short period of time. I'm going to run them here, although they were like the generation they took on production. The alerts were generated over a time period of 5 minutes or so. I'm going to run them like immediately with a 50 milliseconds delay, so we don't have to wait. So let's run this. So this is done. 31 events have been sent to iAlert. Let's switch to the alerts overview. And as you can see here, we have literally 31 new alerts. So none of them were grouped. And this is exactly the way how they also were created in production. And some of them, like at first sight, they look similar, like things like black box, probe, HTTP failure. On different instances, some of them were on the same instance. So yeah, and then some of them are clearly like other issues. For example, there is an alert regarding a RabbitMQ node that's down. So let's now try the same example with alert grouping enabled. For this, I'm going to modify the alert source settings in iAlert and enable alert grouping. And there is a default grouping window, which like doesn't matter for our purposes right now. So it's 5 minutes. So it will the alert grouping will always happen during the selected window. And there is another important parameter. It's the similarity threshold. And I'll be talking later in the presentation what exactly this threshold means. But here, to show you the effect of setting the threshold, we have a small preview. When the threshold it's a number between 0 and 1. And if it's closer to 1, then fewer alerts are grouped. And if it's very low, then almost all the alerts are grouped. And we're going to leave it at the default of 0.75. And here, you have an idea based on the past alerts, how this grouping will affect future alerts. Okay, so let's save this. And now let's run the same runner again. So we are again creating 31 alerts. But this time I actually forgot to resolve the previous alerts, but it doesn't matter. So if we go to the alert overview here, we can now see that previously we had 31. Previously we had 31. Now we have 34. That means only 5 new alerts have been created. And you can see here, there are many alerts that have been aggregated. For example, these black box probe HTTP failure alerts, they have been aggregated because there are many alerts that are semantically similar to this alert, and other alerts, to the contrary, are not aggregated. For example, this hardware server status is not healthy. You know what I'm going to do? I'm quickly going to resolve everything so we get a clean slate. So it's clearer how many alerts you would end up with when you have intelligent alert grouping enabled. So let's do this again. So it was empty. Now we have submitted again 31 new alerts. And instead of having 31 alerts, we now have 6 alerts. So as you can see, these also work with real alerts, production alerts. And yeah, it's capable of understanding, in this case, for example, it's probably because the black box probe HTTP failure is probably because there were completely different instances. And it actually looks at the entire payload. And I'm going to explain later what pre-processing is involved before we use AI to do the deduplication. But this problem, for example, is clearly a completely separate problem. Hardware server status is not healthy, is also a separate problem. And this some firewall outside subnet running out of IPs is also a completely different problem. So that was the demo. Now let's move back to the slides, and I would like to walk you through how you can build the exact same behavior into either your alerting system, or maybe even use it somewhere else with a similar use case. All right, first I'm going to talk about a few concepts that are required to understand the overall process, how we've built this. Let's start with vector embeddings. Vector embeddings, a vector embedding is a mathematical representation of any kind of data in a high-dimensional space. So where each vector represents a specific kind of data, could be a word, could be an entire sentence or an image. And this piece of data is essentially transformed into a vector, and a vector is a point in a high-dimensional space. And these vectors or points in this space, they capture the semantic relationship to each other. So the closer two vectors are, and we measure this by using distance functions, mathematical distance functions. And the closer two vectors are in that space, the more likely is it that they refer to the same underlying concept. And these embeddings are used almost anywhere in AI applications. When you, for example, use ChatGPT, your prompts are transformed into a series of numbers first. And similarly, we will also transform alerts into a series of numbers. An embedding model is a special type of pre-trained machine learning model that learns to represent complex data such as words, sentences, images in a lower dimensional space. So this is actually where most of the magic happens. We use these pre-trained models to transform alerts into these vectors. And once we have everything in place, we can set up our alert deduplication pipeline, which consists of 3 steps. The first step is we pre-process the alerts. And the second step is we turn these alerts into vectors using an embedding model. And then we apply the deduplication logic, which I'll get to in a second. So let's first start with pre-processing the alerts. Pre-processing involves normalization and cleaning. During normalization, we just make sure that all the alerts that we have, they follow a common format. And for us as a platform that sits on top of many observability and monitoring tools, this is more or less already the case. So we integrate with 100+ tools, and we turn all these alerts into a common format. And in the cleaning phase, we're going to remove everything that's not required for the task at hand. Like, for example, if your alerts have unique IDs. Unique IDs, they don't play a role when you want to answer the question, are 2 alerts the same or not? Because the IDs will differ anyway. Or we're also going to remove any syntactical elements. For example, if alerts are represented in JSON, we're going to remove all of the JSON elements and reduce the alert to essentially plain text. This will not only reduce costs or reduce tokens, which are the primary cost driver when using and developing LLM apps, but it will, again, just remove everything that you wouldn't consider for deduplication. And then we vectorize these plain text documents using an embedding model. And in our case, we use a self-hosted embedding model, but you could use one of those general purpose embedding models provided by OpenAI, for example. So they have APIs for their text embedding models, and you could use those. The reason why we're using a self-hosted model is because for us, this is a high throughput use case, right? So we're processing millions of events on any given day, and we don't want to introduce an external dependency where we have to make an external HTTP call just simply for performance and stability reasons. Therefore, we've selected one of those embedding models that are available on Hugging Face, and in this case it's a general purpose model that was trained on a wide variety of text, including common data sets such as Wikipedia, but also where data from Stack Overflow was used, for example. And that's why that general purpose model is also capable of capturing technical content. And then once we transform the alerts into vectors, we store them in a vector DB. This is of course optional, but storing them in a vector DB is more efficient because vector databases are optimized for storing and, more importantly, managing vectors and querying vectors. And one operation we're going to use is calculating the distance between vectors, which will represent our deduplication logic. We have an incoming alert flow. Every alert is vectorized and stored into the vector database. And for each incoming new alert, we're going to query our vector database and see within a time window of, let's say, 5 minutes, are there any vectors that are close to the one that we're looking at right now? And this closeness is measured through a similarity function. It could be any similarity function that measures distance between vectors, for example, a cosine similarity. And then we set a threshold. So this distance metric returns a number between 0 and 1, meaning vectors are essentially the same, are very close to each other. And 0 is they are very far away from each other. The main advantage of this approach is that we're capturing the underlying semantics of an alert instead of looking at their textual similarity. And you can even use this if you're monitoring your service on multiple levels. You can use intelligent alert grouping across multiple monitoring and observability tools. Things that you have to consider are, of course, selecting a model that's appropriate for your domain, and then just making sure that it works as expected, because these models, they can behave differently. For example, if they weren't trained on non-English data, they might behave differently if your alerts are not in English, for example. And of course, looking at the threshold, playing with the threshold, because the threshold itself, that doesn't mean anything. So a threshold of, for example, 0.75 could be perfectly fine for one specific area, but for another, you might want it to have in 0.9. And I showed you one way to do this is just testing the threshold on past alerts, where we used the slider and simultaneously updated the grouping based on the past alerts. And then last but not least, we do also provide or collect feedback on all alerts. So it's a simple thumbs up, thumbs down, where you can say, okay, this was correctly grouped or this was falsely grouped. And we make these metrics transparent. And based on these metrics, you can further fine tune the model. All right, thank you for listening. We do have a dedicated guides for AI and incident management, which also covers the other use case that I briefly hinted in the beginning of this talk. Feel free to scan the QR code and download this guide. These guides are also available on guides.alert.com in HTML version, where you don't have to download a PDF. But if you're more comfortable with PDFs, just scan the QR code and download the PDF guide for you. This is an online conference. I'll be around. If you have any questions, feel free to drop your question in the Slack channel. Thank you.